today I want to sort of take a step back to the conservation of momentum and the Bernoulli equation and revisit those again, because we could extend our previous discussion with some things that we sort of left to the side, and I think it'll make it more complete. So first of all, recall the momentum equation. The simplest expression, the simplest form for the momentum equation that we had was for steady flow with uniform velocity in all the cross sections, right? And 1D, so we could sort of have easily inlets and exits of fluid where we could account for the momentum. And we wrote that as sum of forces equals to basically the sum of the momentum fluxes across all of the control surfaces. Momentum in, momentum out. This was our simplest form for steady, uniform velocity across the control surfaces, uniform velocity and all the other quantities, right? Uniform density and so on. Now, what if the control volume is moving? Well, we can use the same exact equation, but we want to, instead of using the velocity of the fluid only, apply there the relative velocity between the fluid and the control volume. So it's not any more difficult. But the velocity has to be the relative velocity. Between the fluid and the control volume. So let's look at an example. Suppose that we have some sort of nozzle. Okay, the nozzle is fixed to the ground, and we have fluid going in, coming out in the form of a jet, and hitting say a vein, but the vein which deflects the jet vertically upwards is allowed to move and let's imagine also in addition that there is some friction here against that movement. The whole vein, or it's a sort of like a moving block, is moving with a velocity v, B for box. The nozzle is stationary, so we have a stationary nozzle, a moving block which deflects the jet by 90 degrees as shown in the sketch. And let's give some numbers here. We have, this is going to be water flowing here, and the jet area is 5 square centimeters. The velocity of the jet is going to be equal to 50 meters per second, and the velocity of the block is going to be equal to 25 meters per second. For water, let's consider density equals to 1,000 kilograms per cubic meter. And the question is, find the frictional force acting on the block. Okay? So what do we do? Suggestions? Well, we will have to use that, but more fundamentally, what do we want to apply here? Conservation of momentum, which also will include some force balance. So both of them, right? We're going to draw a control volume and do both our free body diagram and also a momentum diagram. So let's imagine now that we're looking only at that block which deflects the jet. And let's imagine that we're also going to draw a control volume which includes the water jet. So the water really only enters the control volume perpendicular to the controlled surfaces. Here's our control volume. And we have, of course, some forces here. We have the friction force, which is what we want to find. And we have a normal force, which opposes the weight there. We also have momentum fluxes. So I'm going to do the two diagrams in one, the free body diagram and the momentum diagram, because this is easy here. We have only two momentum fluxes, the m dot velocity of the jet coming in here and m dot velocity of the jet coming out there. I think it's a bit crowded, so let me rearrange some things here. And the velocity of the jet should be the same because we assume that, of course, the jet in this small distance doesn't change diameter, so continuity of the jet indicates that m dot Vj is going to be the same, just pointing in a different direction. Yes, question?
The jet area is 5 centimeters.
Oh, okay. Yeah, it is centimeters. It's just my handwriting is not very clear there. 5 centimeters squared. Good. So we choose an inertial reference frame moving with the block. And we do our sum of forces in the x direction. Basically, in the x direction, the only force we have is F pointing in the negative x direction, so minus F. And we have only one momentum component in the x direction, which is the momentum going in. It has a negative sign also because the velocity and the outward normal point different directions, right? Always think about the outward, the dot product that was inside our surface integral is what is the origin of this term over here. We just simplified it very much because everything is constant. But if you recall where it comes from, you should be able to recognize how to apply the signs. Here, this dot product that was included here was v dot n, right? So this tells me that the sign here is minus m dot times v, but the velocity here in a reference frame moving with the block is the relative velocity, velocity of the jet minus velocity of the block. Yes?
So are they supposed to be equal to each other or on on the same side of the equation?
No, they're equal. The sum of forces in the x direction is only minus F. There's the only force. And the sum of forces in the x direction is also equal to the sum of all the momentum fluxes in the x direction, which is only the momentum going in with the jet. The other momentum is going out the vertical direction, so it doesn't affect this equation, which is only x direction. So this is what I'm looking for. I just skipped a step, put them both together. So this is just the momentum inflow here. So now we can basically, we have everything, right? So minus F is equal to m dot is minus rho A. Oh, did I skip? No, that's correct. So minus rho A times V, right? But here I have V again. So V is always the relative velocity. So I'm going to get V jet minus V block squared. So it's everything the same as we've done before. The only difference basically is that we're using relative velocity. So now we can calculate this. I'm getting rid of those minus signs on both sides of the equation. 1,000 kilograms per cubic meter. Oops. Oh yeah, it is cubic. And the area is given 5 centimeters, but let's move it to meters squared. So times 10 to the minus 4 meters squared. And the velocity of the jet minus the velocity of the block is 50 minus 25 meters per second squared. And so now we can obtain the result. It is 312 Newton. That's our final result. So all that we've applied before is useful in this case. The only difference is that we need to take care of the fact that we need to use a relative velocity, and the control volume moves with, in this case, the vane. Yes, a question?
With the velocity and the normal vector, what is the normal vector perpendicular to?
The outward normal. So always the normal is a unit vector that points outward of the control surface. So it will always be, the dot product would always be positive with things going out, like in this case, and negative with things going in. Yeah? Any other questions?
So although you have the velocities going in the same direction, it's that dot product that makes the velocity due to the jet negative the other way.
The velocity doesn't change sign, but the sign of the momentum takes the sign of that dot product. When the outward normal is pointing the opposite than the velocity, you get a negative sign from the dot product. So remember, dot product of two vectors is the magnitudes multiplied the cosine of the angle, and in this case it's -1 because the angle is 180 degrees. So that's where it comes from. Okay. Oh, I should have called this a normal force. We're not doing it in that direction. There would be a weight and a normal force. I guess my mind was there playing tricks on me. This is just a normal force. If I were to do a momentum in the other direction, I might, but I don't need that, right? Because I was being asked. It would be positive if it's going out. Yes.
So in this case, when there's a flow, you don't consider the force that the flow is acting on the body. Or is that? I'm just confused how the only force the friction is the only force in the next direction.
Because what we're calculating are the forces on the control volume, and the jet and the block are both inside the control volume. Everything that's inside the control volume is like a black box.
Okay, so
The control volume is this technique that allows us to bunch everything that's inside and not look at it, and consider the flow going in, going out, and the forces acting on the control volume, and that's why it's such a powerful method.
As for instance, there was displacement of water into the system and create force.
Yeah, that's the force that we're calculating.
That's friction. It's under
Well, the reason why there's here this frictional force, remember this block is moving with a constant velocity. So if there was a net force, there would be some acceleration. There is no acceleration here. So the sum of forces is 0. Right? That was, everyone clear now? Okay, good. So now, what if the control volume is accelerating? Next question. Obvious. Next question. Since that brought to your head that problem. Well, in that case, the problem no longer can be modeled as a steady state, which is what we've assumed before. We were using the equation of momentum for a steady state. So now we cannot do that. So let's think about the problem we've just done, but instead of the there being a friction force, which made everything balance out, suppose that there is no friction force. So now we have the wheel vane that we had in the previous example, and it is again hit by a fluid jet, with the velocity, say v of the jet, and there's no friction force. So the question now is, what would the velocity of the cart be? The box, the whatever we call it, block, vane. So now the velocity is going to be a velocity with respect to time, because there's acceleration. The velocity changes. So now we must retain the unsteady term in the momentum equation. So sum of forces, let's retain also the vectorial form of the equation, is equal to this unsteady term, the derivative with respect to time of momentum, mv, and the control volume, plus now the terms that we had before, which are the fluxes of momentum in and out of the control volume, sum of plus or minus m dot v. Now here there's no friction force, so the sum of forces equals to 0, but we still have the unsteady term, and the fluxes. But this has to be equal to 0. Now these fluxes are the same ones we are calculated before. So this is going to be minus, in the horizontal direction, minus rho A V jet minus V of the block squared. Same flux term we already calculated in the previous example. So we have, and the mass is constant, and the derivative applies to the velocity of the block. So I'm going to write m dv block dt equals, and I'm taking this term to the other side, so the sign goes away, rho A v jet minus v block squared. So basically we have an ordinary differential equation for the velocity of the block. We can separate variables and integrate. D of velocity of the block divided by, I'd take this term that has velocity of the block to the other side, equals to rho A divided by m dt. Now I can integrate. The integral of this term is 1 over v jet minus v block, and here we have rho A over m times t plus a constant of integration. To find the constant of integration, we need to apply some initial conditions, and so we could perhaps have that the velocity at time equals 0 is 0. The block starts from a stationary situation. So I've ran out of space here. Let me see. I've integrated that. That's right. Integrate, so that's why I reduced that. Yes? Yeah, but the block also has a minus, so those minus cancel out. There's two minuses, yeah. You can always check it by taking derivative of that, right? So the derivative, we have v jet minus v block to the power minus 1. So the derivative of that is minus 1 times v jet minus v block to the power minus 2. And the derivative of the argument of that is minus 1. So the two minuses cancel out. You see that? Let me make a little space around here to finish that up. So let's consider that the velocity of the block at time equals to 0 is equal to 0, and so we can find the constant now, and it gives me that constant of integration is equal to 1 over v jet. Putting it over here, with time is equal to 0, this is 0, constant equals 1 over vj. And so our answer for the velocity of the block is that, well, it is a function of time, so let's write down explicitly, it's a function of time, and it's equal to velocity of, so now we would have to sort of do a little algebra, but I'm not going to do that. You can check it in your own time. I'm just going to write down the answer. V jet t over m, that's the mass of the block, rho a Vj plus t. If we were to make a plot of this, it would actually look something like this. The velocity of the jet the velocity of the block would go asymptotically to the value of the jet. As time tends to infinity. Which makes sense, right? Block starts accelerating. You hit something with a jet, it'll start accelerating and asymptotically approach the velocity of the water itself, unless there's some sort of opposing friction, like in the previous example. So the classic application of this situation is the equation of motion for a rocket. We have studied the rocket before, but we had a little rocket that was attached to some sort of launch pad, and it wasn't really moving, right? So we were just calculating the force on that launch pad. That's the only thing we've done with the rocket so far. But what is interesting of rockets is to be able to calculate its motion due to the propulsion, right, that is generated by the rocket engines. So how we apply that to the rocket? Classic example. So the situation with the rocket is you have a rocket moving vertically upwards. In this case, it could be moving at an angle, but we're going to start with the vertical situation just to make it less complicated. Rocket moves vertically upwards with a speed that I've written here, Vr, with respect to the ground. We have some exhaust gases coming out, leaving the nozzle. So let's write that the nozzle has an area, say, AE for exit, for the exhaust, if you will, exhaust gases. We have exhaust gases leaving the nozzle with a speed VE for exhaust relative to the rocket. And suppose that it's also leaving with some sort of overpressure. So there is a pressure of the exhaust here, PE, for the most general case. So the goal is to obtain, of course, the equation of motion of the rocket. So how do we do this? Well, first we're going to draw a control volume. Let me draw it on top of this guy over here. And I draw my control surface, so the velocity of the jet is perpendicular. Here's my control volume. And we have, well, in the most general case, we could have some drag force. Let's write a drag force here, D. We also have the weight of the rocket, weight. And we have some pressure force, because we've said there's a pressure which is not zero. So I'll put it over here. PE, AE is the pressure forces. So D is a drag force. We have the weight. And we're going to consider a possible pressure force for an overpressured jet. So suppose that our coordinate is z, positive pointing upwards. We have our control volume, and the control volume is moving with the rocket. So the sum of forces in the z direction is P E A E is positive, minus W negative with respect to our coordinate, and minus D. And there's only one momentum flux out of the control volume. The momentum flux is out of the control volume, and it is m dot v out. I'm going to write it, which is the speed. V out is the speed with respect to an inertial reference frame now. And so that's going to be m dot velocity of the rocket minus velocity of the exhaust gases with respect to, abbreviated, an inertial reference frame in the ground, and there's also an unsteady term, like in the example we've just done with the moving block. So there's the unsteady term is like an accumulation of momentum in the control volume. The control volume is accelerating. So finally we can write our momentum. Okay, this is the unsteady term. Well, we can write the whole equation. Sum of forces in the z direction is equal to, let's put the unsteady term here, m of the rocket, velocity of the rocket, plus the momentum out minus momentum in. Again, those signs are, as we discussed before, due to the product, the dot product between the velocity and the outward normal. And so finally we can write the momentum equation by putting all these things together. P, the force, the sum of forces we already have here, P exit area, exit minus the weight minus the drag is equal to the unsteady term, mass of the rocket, velocity of the rocket, and we don't have, we only have this term here for the momentum flux, m dot v rocket minus velocity of the exhaust gases.
When you do this, I have to take into account that the rocket's getting lighter as
That's because the mass of the rocket, I have it inside of the integral, so I haven't taken it out yet as a constant. So now, indeed, you're correct. We have to consider that, and therefore this time derivative here includes both. We can apply here our product rule and write m of the rocket times dv dt of the rocket plus velocity of the rocket times dm dt, because indeed the mass is changing. And now, well, I'll wait for you to take notes of that, and I'm going to need a full extra slide with some workings, so I'll give you a couple moments more to take that down. Some of you are still everyone clear so far? Good. All right, so let's continue. We had that term that had included the derivative of mass as was pointed out. But let's use conservation of mass. And that's going to indicate that, of course, the derivative of the mass with respect to time has to be related to the fluxes. I mean, it's the same equation. We have the unsteady term and we have the fluxes. And the fluxes here are only mass going out. That mass going out is m dot. So this is equal to 0 because mass cannot be created or destroyed. So basically this term is simply mass flow out, or from the actual full equation we had the sum of mass flow out minus mass flow in the equation, but there is no mass flow in, so this term cancels out and there's only one of these. That is where this comes from, the continuity equation. So now we can put this back into our momentum equation. We had PE, area of the exhaust, and we had minus weight minus drag equals 2. We had mass of the rocket and dv dt of the rocket, and then we had this term that had, from the product rule, velocity of the rocket times dm dt. So for the m dt I can write minus m dot from the continuity equation, okay? And then we had the other term that was plus m dot vr minus v exit. So one of these is going to cancel, basically this is going to cancel out. This one with this one cancel out, right? Because this minus sign comes from taking this minus to this term to the other side. I've written dm dt as minus m dot from the continuity equation here. So I've used the continuity equation to write this term. And this one was still in the previous equation, so there's nothing new there. But you see that now I can cancel these two out. And so I can write, let me rearrange a little bit. I'm going to put this one on the right. This one remains. And the m dot ve remains. But I'm going to rearrange them a little bit. So I'm going to write mr dvr dt. I'm going to leave this one and put everything else on the other side equals. So this one has a minus from the minus VE. I'm going to take it to the other side here. M dot VE. And we have plus PE AE minus weight minus drag. This we're going to identify with the thrust of the rocket. If the pressure, the overpressure of the rocket, if it was a free jet, then this pressure would be atmospheric pressure and this term would be 0. And we would just have m dot v exit. But we leave it here because in a more general case, the jet might be overpressured. Okay? This is the thrust of the rocket. We call it T. It's a velocity thrust plus a pressure thrust. Possibly, which could be 0 or could not be 0. So if for the moment we were to neglect just for the moment, to see what happens, neglect the drag and weight components, which could be reasonable if we are sort of in outer space, or already coming out of the atmosphere of the Earth, where gravity might be very weak, perhaps, and drag might be very small because there is no air. So there are situations when this would physically apply. So for the moment, neglect weight and drag and see what happens. Okay, we get, well, the thrust, T is equal to mr dv r dt, a much simpler equation. So let's write the instantaneous mass of the rocket as mass of the rocket is equal to an initial mass, m initial, minus m dot t. the initial mass at the time of ignition will be the mass of the rocket and all the propellant fuel in it. And as time evolves, just the propellant is going to be burned out and come out as exhaust gases. So that makes sense. We write it this way. So T is equal to m initial minus m dot T time and dVr dt. So now we separate variables. And we have T thrust dt of time, right? And take this to the other side, m initial minus m dot T equals to dVr. Now integrate. The integral of 1 over x's logarithm. So we have T, thrust, and we have the integral of 1 over T with some sort of coefficients there, including a minus sign. And so the minus sign is the one I'm worried about, minus the logarithm of m initial minus m dot T, and divided m dot, because the m dot is multiplying the argument here, time, which we're integrating, and plus a constant equals velocity of the rocket. To get that constant, we apply some initial condition. In this case, it's logical to use that the velocity of the rocket is 0 at time equals to 0. And we get our constant. Velocity of the rocket at time equals to 0 is equal to 0. And so I get that the constant is equal to thrust divided m dot times the logarithm of initial mass. Yes? Good? Now we're going to put those things together to write the final equation. Good? Almost done. But I've run out of space, so we want to keep using this same here, otherwise it's a little bit confusing. So let me do my trick of making some extra space in this way, if you have a bit of patience, because otherwise it's hard to reference our previous results. Okay, so now we put those things together and we got that the velocity of the rocket is, well, of course, a variable of time, and we have T over m dot multiplying everything, and we have the logarithm of this product and the mi here, right? But which one has the minus? This one has the minus. So it's mi over mi minus m dot T. Or another way that we could write it is T over m dot logarithm, logarithm ln of m initial over m final, because this is like the final mass at any point in time, the initial mass minus what's been burned out, right? So this one is actually known as, one moment, so Tsiolkovsky, this is a Russian guy, so let's see if I got this correct. Tsiolkovsky rocket equation. And this mi minus, over mf is the mass ratio. And the ratio T over m dot is called the specific impulse. In rocketry, it has units of velocity. No, because of course logarithm mi, mf, this doesn't have any units. So the specific impulse has units of velocity. Yes, you have a question?
How can we make that constant?
The constant is added in, but we already calculated it. And it's here, T over m dot logarithm of mass initial. The other term is T over m dot logarithm of, and I just put the two logarithms together because, got it? So let's do a numeric example. Let's see, what time is it? Let's take a little break and then we'll do a numeric example. 10-minute break.